Spatially resolved diffraction analysis. Optical microscopy provides local information on the grating in the context of geometry and dimensionality. No information on the optical functionality, such as on the Bragg selectivity, is provided. However, this information is accessible according to the relation between structure and function and can be derived from spatial resolved analysis. In case of transmission-type gratings, this can be accomplished by means of scanning the lateral plane to obtain local values of the grating parameters. Local values of thickness d, refractive index contrast delta n, as well as grating period lambda and the grating slant phi can be obtained. The lateral scan method is keeping track of the hologram shape, which is determined by the material response to the Gaussian intensity distribution of the recording beams. Probing only a fraction of the exposed area is primarily for the purpose of measuring precision. However, it also enables scanning of the grating by moving the sample perpendicular to the optical axis. A sequence of rotation scans through the grating diameter constitutes a lateral scan. This analytical method allows the determination of the hologram characteristics along the sample surface. Thereupon, it is possible to compare and track respective properties from the center of the grating to the edges, corresponding to the areas of highest and lowest recording intensity. As a consequence, spatial sequences of the grating parameters are derived, providing insight into the local material characteristics. Figure 9 illustrates the principle of lateral scanning. The ratio of probe beam to exposure beam diameter was 1:6. The local diffraction efficiency is displayed along the lateral position of 5 different volume holograms. The gratings were recorded with different exposure dose. The respective energy density of exposure, E, is displayed in Figure 9. The lateral scan reveals the material response, resulting in overmodulation, nu greater than pi2, in case of E greater than 330 mJ/cm2. Principle of lateral scanning: holograms were recorded with exposure beam diameter of 3 mm and scanned step by step with a probe beam diameter of 0.5 m. 5 lateral scans are shown. The corresponding gratings were recorded with different exposure energy densities. The results from spatially resolved investigations of the grating constant reveal the influence of the recording intensity and exposure duration on the Bragg selectivity. The advantage of lateral scanning consists in the exploitation of the Gaussian intensity distribution of the recording beams. Thus, lateral scanning provides direct access to characterize the material response, based on one single exposure. As a result, other influential factors on the material response, such as pre-exposure, are eliminated.